So in this series of videos, we are going to start to learn, apply the laws of thermodynamics to chemical and phase equilibria. Let's begin by discussing what chemical equilibrium is and what phase equilibrium is, and how are we going to treat mathematically from the principles of thermodynamics. Chemical equilibrium is established when the rates of a forward reaction and its reverse are equal. This is very frequently encountered in industrial chemical conversions, especially in ammonia synthesis reaction. Ammonia synthesis reaction is a particular reaction where it is mildly exothermic. However, due to this mild exothermicity, the forward reaction rates are very slow under moderate temperatures. As a result, we need to run this reaction at higher temperatures. While running this reaction at higher temperatures, we encounter limitations from thermodynamics. In other words, the equilibrium conversion of this reaction diminishes as we increase the temperature. So establishing what our equilibrium conversion is an important problem when we are designing or operating ammonia synthesis reactors. We will learn how to estimate those equilibrium conversions from the principles of thermodynamics. All right, so this is chemical equilibrium. On the other hand, we have phase equilibrium. In chemical conversion processes, we produce chemicals which we separate through methods of vapor-liquid equilibrium. If there are differences in the boiling points of the components, such as between ethanol and water, all right, if we synthesize ethanol through fermentation, and if we would like to purify ethanol, we need to distill ethanol from water. Ethanol has a sufficiently lower boiling point than water. As a result, we can boil the mixture, and the lower boiling component is enriched in the vapor phase, as indicated by the vapor-liquid equilibrium phase diagram you see on this corner of the board. And by carrying out cascades of operation that we separate ethanol from water to a certain extent. We will learn what that extent is. So we have to get a general understanding of equilibrium, how it is related to multi-component phase equilibrium, how it is related to chemical equilibrium, and other aspects of chemical conversion processes. But before we can go into the multi-component systems, let us remember the equilibrium of a pure fluid with its vapor. Equilibrium of a pure liquid with its vapor. Now, this is a subject we have touched upon in Thermodynamics 1 content. We have videos for equations of state and for estimation of vapor-liquid equilibrium for pure components. We will refer you to those earlier videos, but we will have a very brief review of what that was. Now let us first start by drawing the PV diagram for a pure fluid. So here we have intensive volume, here we have the pressure, and this PV diagram looks something like this. And this volume scale is a logarithmic scale. Be careful that this is a logarithmic scale. On this side we have pure liquid or saturated liquid. On that side we have saturated vapor. And our isotherms, let me use a different color. Our isotherms, the constant temperature curves, the real physical processes go like this. We have a critical temperature isotherm that goes like this, goes through a saddle at the critical temperature. And this is the vapor-liquid equilibrium curve of a pure fluid. Now, we have discussed in the earlier videos, the details are there. I recommend that you go back and review those videos, but I will also go over them one more time here. So these equations, these curves are describable by cubic equations. Simply describable by cubic equations. And cubic equations have the functionalities that can very well describe the sharp decrease at the liquid domain, a reciprocal relationship at the vapor domain, and we have an interesting behavior that our system goes through, and we are going to make sense out of the behavior that our fluid encounters in these domains, whether they are real or they are mathematical realities that has no physical connection is going to be clear after we start deriving our equations. Now here, at this temperature, this curve says that the vapor pressure of this fluid is this. This is measured experimentally. We keep the liquid at a constant temperature. We have a system that sustains a pressure or that sustains, that measures a pressure until the liquid phase has sufficient vapor to saturate its vapor. In other words, if you have a closed container, we add a certain amount of liquid in this closed container. We have a pressure measurement device that is going to measure the pressure, and also we have facilities to maintain a constant temperature, facilities that exchange heat so that we can maintain a constant temperature. So our fluid, of course, in the gas phase, we evacuate it. Let's have a complete system. So we have a vacuum pump here. All right. We have evacuated the gas phase, so we have no interference from other molecules. And the practically zero pressure domain has its liquid in it, and the liquid molecules start to evaporate and populate the volume that is not filled with liquid. And these vapor molecules, depending on the temperature, dictated by the heating elements, will have a certain level of population. That temperature will allow only a certain number of molecules in the gas phase. We will see why. And that certain number of molecules in the gas phase will exert a certain pressure, which we indicate by the vapor pressure. So we kept the temperature constant. We have a vacuum pump. We have decreased the pressure. Our liquid started to boil. It boiled until everything is vapor. No liquid remained. We kept evacuating, and we have now a reciprocal relationship. If you remember, that reciprocal relationship is due to the ideal gas behavior. And when we were trying to have a mathematical relationship, we did not forget the limitations of the ideal gas law. We derived a new equation of state by removing the limitations of ideal gas law one by one. So let's remember what those limitations were. The ideal gas law was something like this. P times specific volume is equal to R times T. And it had two limitations. The first limitation was that volume occupied by the molecules were negligible at very low pressures. If the gas phase is not very dense, the volume occupied by the molecules could be neglected. And the second assumption of the ideal gas law was that the molecules did not interact. Then we removed those assumptions. All right. First, we introduced the volume of the molecules. The first approximation was removed. So B, standing for the volume of the molecules, was subtracted from the total volume to have a better accurate representation of the prediction of this equation of state. All right. But still, this equation of state has a simple reciprocal relationship between pressure and volume. That simple reciprocal relationship between pressure and volume is more evident for the temperatures that are greater than the critical temperature. This is a reciprocal relationship. And this reciprocal relationship doesn't give us a vapor-liquid equilibrium. You see that singularity between a liquid in equilibrium with its vapor is not observed under those conditions. Even this equation doesn't make much difference. This equation with this B term in it just shifts our curve slightly, but it doesn't give us a singularity representation. All right? In order to have that, we have to apply or remove the second assumption. Pressure is equal to RT over V minus B minus A over V square was our first approximation of an equation of state that represents the fluid behavior in the two-phase region. All right? So this equation is called van der Waals equation of state. And the van der Waals equation of state, when you equate the denominators, it's a cubic equation of state. So when we have a compressibility factor equivalent of this equation, so I strongly recommend that you stop this video and derive the compressibility factor equivalent of this equation of state, which is going to look like that. It is going to be equal to 0. There we have our cubic equation, And from the roots of that cubic equation, we can now start constructing our liquid vapor envelope curve. But before we can do that, let's review the concept of equilibrium. So here in this chamber, I have a liquid domain, I have a vapor domain. I will call this liquid domain domain 1 and vapor domain as domain 2. All right, this is the liquid domain, this is the vapor domain, and I will ask a couple of questions in that domain to check a condition, to find a condition that allows me to judge that, yes, this process is at equilibrium. Now we are going to remember the first law and the second law expressions for a closed system. For a closed system, the first law simplifies to and the second law corresponding to this closed system this is the entropy balance, and the second law statement is that entropy generation is always greater than or equal to 0. So we have those three equations that are going to guide us towards defining the equilibrium conditions. In this closed system, let's have a chamber with two domains. All right, domain 1 and domain 2. We have a certain constant total number of moles of fluid in this chamber. Okay, and in this chamber, this is a constant volume chamber and is isolated from its environment. Since this chamber is at constant volume, this term drops out. And since it is isolated from its environment, this term drops out. That we have du over dt is equal to 0, or u is constant. All right? And we have in domain 1, n1, u1, s1, right? Those are our state variables. We have n2, u2, and s2. And we will let the system evolve into a state of equilibrium. All right, so this system is evolving towards equilibrium under constant volume and no heat exchange constraint. Constant volume and no heat exchange constraint. So as a result, we know that du over dt is equal to 0 in the system. Number of moles are constant, therefore dn over dt is equal to 0. And we have ds over dt to be equal to S generated. S generated has to be greater than 0. As a result, ds over dt to be equal to S generated, and this has to be greater than or equal to 0. All right? The second equation, the first one is that internal energy, or total internal energy, is constant. The second equation says that entropy has to be maximum. So this is our constraint. So in this system, we have n that is equal to n1 plus n2, u being equal to u1 plus u2, v being equal to v1 plus v2, and s being equal to s1 plus s2. All right? So we have a system with constant internal energy and constant volume, arriving to an equilibrium state where entropy becomes maximum, and we have a condition that justifies the molar exchange between two domains, energy exchange between two domains, volume exchange between two domains, that this boundary can move, and entropy exchange between those two domains. So we're going to have our constraint, entropy to be maximum, and we're going to define entropy as entropy of internal energy, volume, and number of moles. All right? Entropy is a function of internal energy, volume, and number of moles. So this entropy, if it is going to be maximized, its derivative should be equal to 0. So let's derive what the derivative of this entropy is. ds is equal to, we're going to remember from what we have learned in thermodynamics 1 as del S over del U at constant V and N times du plus del S over del V at constant U and N dV and del S over del N at constant U and V times dN. You may remember from the opposite expression that U was U of SV, and in this video we started to introduce N as a variable, and du was TdS minus PdV plus mu dN. Mu was the chemical potential, this was del U over del N at constant pressure, at constant entropy and volume. And we have equated this to del G over del N at constant temperature and pressure by the change of a coordinate. This was the expression for the internal energy, and temperature was del U over del S at constant V and N, and minus P was del U over del V at constant entropy and N. So we have U equivalent of the expression if we flip this equation so that we have entropy as our dependent variable and internal energy, volume, and number of moles are our independent variables. Our expression looks like this. ds is equal to 1 over T du plus pdv minus mu dn. We just moved these to the other side and divided them by t. So now we can derive each of these expressions. Del S over del U at constant V and N is equal to, V is constant, N is constant, del S over del U at constant V and N is equal to 1 over T. This term is 1 over T. Del S over del U, del V at constant U and N is equal to P over T and del S over del N at constant U and V is equal to minus mu over T. So now we have our parameters. We're going to write this expression for domain 1 and domain 2. We're going to look for where it is a maximum. So when we combine what we have derived together with our equation for the entropy, we have ds to be equal to 1 over T du, P over T dV, minus mu over T dN. So this term is the Gibbs free energy. Partial molar Gibbs free energy. We will encounter this term very frequently in this course. Let's get used to it. Let's call this a G over T instead of mu over T. All right? So we are going to generate our balance equations for phase 1, domain 1, and domain 2. Let's do that. ds1 is equal to 1 over T1 times du1 plus P1 over T1 times dV1 minus G1 over T1 times dN1. Same thing can be written for phase 2. ds2 is equal to 1 over T2 du2 plus P2 over T2 dV2 minus G2 over T2 dN2. All right. So when we sum them up, we're going to get the overall process entropy, and we're going to relate overall process entropy to the state variables of temperature, pressure, and Gibbs free energy. So when we sum these two terms up, we get ds, which is equal to ds1 plus ds2 for those two domains, which is equal to 1 over T1 times du1 plus 1 over T2 times du2. I will leave this one here, plus 1 over P1 over T1 dV1 plus P2 over T2 times dV2, leave this one here, plus or minus G1 over T1 times dN1 minus G2 over T2 times dN2. Remember, we've had the total internal energy to be constant. It's right here. U is equal to U1 plus U2. du, which is constant, therefore 0 is equal to du1 plus du2, or du1 is equal to minus du2. Similarly, from the constant total volume, we get dV1 to be equal to minus dV2, and from constant number of moles, we get dN1 to be equal to minus dN2. Right? Derivation of dV1 equals to minus dV2 and dN1 equals minus dN2 are the same as we derived this du. Okay? So I'm going to substitute one for the other. I will go for 1. All right? I rewrite this equation as 1 over T1 minus 1 over T2 times du1. Right? I substituted 2 for 1. 1 for 2. Plus P1 over T1 minus P2 over T2 du2 dV one, not 2, and then I will substitute for N1 plus minus G1 over T1 minus G2 over T2 times dN1. All right? ds is equal to those combination of terms. Now we are going to start our analysis. Now, at the point of equilibrium, entropy is greater than or equal to 0. So we're going to take the entropy to be equal to 0 at the point of equilibrium. All right? Point of equilibrium is point of stagnation, no generation, no entropy generation. So ds is equal to 0. If ds is going to be equal to 0, all right, either these terms or their multipliers should be equal to 0. All right? We know that at equilibrium, molecules still move around. All right? This molecule goes here, that molecule comes here. All right? Equilibrium is not a complete stationary state. It is that the number of molecules crossing this boundary is equal to the number of molecules crossing that boundary. All right? So, since we are looking at only the first domain, we cannot say that these terms are 0. All right? They are non-zero. The only terms that can be 0 are these terms. And this should be our equilibrium condition. If 1 over T1 minus 1 over T2 is equal to 0, then T1 should be equal to T2. All right? So now the first term establishes that the temperatures in those two domains has to be equal. Now the temperatures are equal. If this is going to be 0, pressures must be equal to 0. Right? T1 is equal to T2. They cancel each other. Temperatures are equal to one another. And from here, we get G1 is equal to G2. Partial molar Gibbs free energy, the chemical potential. Gibbs free energy is the energy that we are going to use very frequently, this term, describing chemical and phase equilibria. So now, let's come back. Look at the equilibrium here. The temperatures of those two phases must be equal. If this is my phase 1, if this domain is domain 1, and if this domain is domain 2, temperatures must be equal. Yes, temperatures are equal. All right? It's on a constant temperature curve. Pressures must be equal. This pressure is equal to that pressure. Gibbs free energies are equal. Gibbs free energy equality requires that these areas are equal, and from this point on, we are going to put that in a mathematical context. So the equilibrium conditions that we have derived so far identifies equalities of temperatures in those two phases, equalities of pressures in those two phases, and equalities of molar Gibbs free energies in those two phases. All right. Equalities of temperatures and pressures are intuitive. We will add our intuition to the equalities of the Gibbs free energies. Now the Gibbs free energy, as we learned already, is for a closed system minus S dt plus V dP, or Gibbs free energy is a function of temperature and pressure. And if it is an open system, it is also a function of the number of moles of the species in each phase. So the equality of the Gibbs free energies around an isotherm, a constant temperature curve, can be traced from the second term because we are monitoring this process at a constant temperature curve. All right? So I'm going to label those points as A, B, and C. A is the point that crosses the liquidus, B is the interim point, and C is the point that crosses the vapor curve. So the vapor pressure information that we are going to obtain from an isotherm of a cubic equation of state will be the sum of the pressure integral between point A to B, V dP, between point B and C, V dP. All right? If the Gibbs free energies of phase 1 and phase 2 are going to be equal, these integrals should be equal. All right? These are the areas under the curves of domain 1 and domain 2. Now, before we further investigate how we're going to take this integral, let's come back and let's see what are the other options and why we are just taking such detailed approach of trying to find the point of Gibbs free energy equalities. Now I will draw a little bit larger version of the same diagram over here. In this version, you're going to see somewhat exaggerated version of this cubic equation behavior. Given that this is the only information that we have, this is for a certain temperature, given that this is the only information that we have, in other words, we have our cubic equation of state that is going to give us this curve, we are looking for the vapor pressure. All right? This is the question. We are looking for the vapor pressure, and when we are looking for the vapor pressure, we know that we should have something that represents the volume, specific volume of the liquid, something that will represent the specific volume of the vapor. And we see that between those 2 points, of extremum, we have infinitely many options for P and T pairs. All right? So for this temperature, we can have infinitely many different values of vapor pressure if our objective is to find a volume for liquid and a volume for vapor. Right? So apparently our problem is a little bit more complex than just simply finding a volume for liquid and a volume for vapor. That complexity simplifies when we have this constraint, equality of the Gibbs free energies. And equality of the Gibbs free energies has to be satisfied by the condition that we are going to have a point on this branch of the curve, this branch of the curve. Let's see if our color shows, right? And on this branch of the curve, but not on that branch of the curve. All right? This is the prohibited zone. All right? We don't look for volumes in that prohibited zone. Why is that? Now, this branch and this branch has a condition that is consistent with the physical reality. What is that condition? As we increase the pressure of the fluids, their volume decrease. All right? As we increase the pressure of the fluids, their volume decrease. Or del P over del V at constant T is negative. On this branch, del P over del V at constant T is negative. All right? So these branches are physically meaningful branches that are predicted by our equation of state. However, on this branch, you can clearly see that del P over del V at constant T is greater than 0, and therefore this is not a stable branch. This is not a stable branch. So we are going to look for the Gibbs free energy minimum or equality, Gibbs free energy equality on the stable branches of these equations of state curves. The simpler approach that we can quickly judge is the point where we find the equal areas. All right, this is called Maxwell's equal area construction. So here we have A1, here we have A2, all right, and we are going to find the point C in the middle. We're going to move this curve up and down the line, the cutting point, up and down until we find the equality of those areas. All right? This requires some graphical approach. It is not immediately straightforward in terms of the derivations, but it is easier to comprehend. That generate a plot of P versus V at constant temperature, which is accessible through an equation of state, such as van der Waals equation of state. Let us write here, P is equal to RT over V minus B minus A over V square, right? So these V's are specific volumes, intensive variables, all right? Using this equation, generate this curve and find a line such that area under this curve is equal to the area under that curve. Or develop a mathematical approach. The mathematical approach is here. We have Gibbs free energy at constant temperature as VdP. We are going to find the B, all right, so that our integral of VdP on one branch is going to be equal to the integral on the other branch. But we have a catch here. Our equation of state is volume explicit. It is difficult to extract volume here, substitute in here, and get this integral. All right? Extract volume, make this equation explicit in P so that we can carry out this integral. So instead, we're going to change the integrand and rearrange these equations. We will come up with a new function that is going to be a little bit more convenient than this expression, and we're going to call it the fugacity. Fugacity means the tendency to escape. Tendency to escape. Right? We're going to stop here, and in the next video we will derive fugacity, the basis, and the application on the phase equilibria, and also we will touch upon some aspects of the stability criteria. One of them relates pressure and volume to one another. We will also look at the stability criteria from the entropy standpoint.